Hello Gators, this is 2.1, defining average and instantaneous rates of change at a point. I want to remind you of two vocabulary words you had in geometry. The word secant. The word secant is a line that intersects a circle in two places versus the tangent line, which only intersects a circle at one place, one point. An Algebra 1 topic, average rate of change. Average rate of change is another word for slope. We take 2 points on the curve and we find the rate of change on there. So since there's 2 points on the curve, we're going to think of this line as a secant line. We're finding the slope of this secant line, and notice that I show you graphically, I show you numerically with a table, and I show you algebraically where we actually use the formula to find the value. I'd like you to look at a movie right now that's going to demonstrate the problem that I want to discuss. This is an automatic door closer, and the gentleman opens up the door. He can open it up more than 90 degrees. He lets go and the door closes slowly so as not to hurt anyone. All right, so let's discuss this, this demonstration. If you push open a door that has an automatic closer, it opens fast at first, then slows down, stops, starts closing, and slams shut. As the door opens, the number of degrees D it is from its open position depends on how many seconds it has been since you pushed it. Okay, now suppose the door is pushed open at time t equal to 0 and slammed shut again at time t equal to 7. While the door is in motion, assume that the number of degrees D from its closed position is modeled by this equation. So this is the equation that models it. And what we'd like to do is figure out how fast the door is moving at the instant when t is equal to 1. That's what we're going to look at. And we're going to do it with average rate of change. We're going to take time 1 and we're going to compare it with time at 1.1. So we're going to look at the average rate of change using this function, and we're going to find that the door is opening about 26.33 degrees per second. If we get even closer to 1 second and do and compare the average rate of change at 1.01 to 1, we're going to find the answer is 30.234 degrees per second. And when we get even closer, we notice that the answer doesn't change much. It's going to be the tenths and ones place is not going to change, and the tenths place is going to change slightly. So the important thing for you to notice is that the time interval gets smaller, but notice the rate of change doesn't change much. And this is because as you zoom in on the point 1/100, the graph appears to be straighter, so that the change in D divided by the change in T becomes closer to the slope of a straight line. And there's a point at which we go right into focus in on that point, and you can see that the difference between the 2 points when they're really close together looks like a line. Okay, so what we're doing is using average rate of change to estimate the instantaneous rate of change. We can't really compare at the point 1 and the point 1. That is not possible. But we can compare at 1 and a point close to 1. And at the very bottom here in yellow, it says there seems to be a limiting number that the values are approaching. Let's take a look at what's happening at time equal to 3. Time equal to 3 is right about here, right about there. And so we're going to take a look at 3 and a number close to 3. Stop the screencast and evaluate this rate of change for these 3 scenarios here, and compare with the answers I'm going to give you. And here are the answers. Again, the time interval is getting smaller, but the average rate of change is staying about the same. Notice it also is negative. Negative means that the number of degrees is getting smaller and smaller. And so that's what's the indication, and that's what closing is. Okay, so this door example is talking about an independent variable, which is time, and a dependent variable, which is an angle. And I'm going to go to the last line. this average rate of change that looks like it's getting closer to one particular number, this limiting value is called the derivative of the dependent variable with respect to the independent variable. Okay, so let's take a look at the formula one more time again. We're looking at 2 points that are very close to each other. They're off by, the input values are off by 0.1. And so our formula can say h, and h is assumed to be a value that's really small. So average rate of change can be written in two ways. One that we were just talking about with the door example, and this represents the slope of the secant line. So here's a good picture. 2 points, and we're letting one point be a and the other point a plus h, and this is the average rate of change. We can also look at average rate of change where we're looking at a specific point, a, f of a, and any point on the curve, and we'll just call it x and f of x. So again, taking the two y's and subtracting them, and the two x's and subtracting them, that is also an average rate of change. Now, when we take the limit as this h gets close to 0, as the difference between this point and this point get closer and closer to 0, when you take that limit, that's going to give us the instantaneous rate of change, which is what we call the slope of the tangent line. Now, in the case of the alternative average rate of change, we don't use h. We use the fact that x, this x right here, is getting closer and closer to a. And when it gets closer and closer to a, then this point wants to get closer and closer like this. So the secant, the slope, becomes a slope of not the secant, but of the tangent. All right, so let's summarize again. Average rate of change is the slope of the secant. Instantaneous rate of change is going to be the limit of the average rate of change, and this will be the slope of the tangent. All right, let's go ahead and do an example where we use both options of the instantaneous rate of change. This one is where we use a little small change, 2 points in a small change. Okay, so I'm going to take the limit as h approaches 0, and the formula says a plus h. So, well, this is our a, and so I'm going to put a plus h into my function. So I'm going to put 1 plus h into my squaring function, and then this says to take the function and put a in it. So this will be 1, and then it'll be squared, all divided by h. So that's what we have. Then we're going to take the limit as h approaches 0, and then I'm going to do some algebra. I'm going to square that. That'll be 1 plus 2h plus h squared minus 1 over h. And I hope this is looking comfortable for you. Let me go to the next screen and I'll go ahead and finish it. And when I finish it, I can actually find the limit, and the limit is 2. Now, the limit being 2, what is this telling us? Well, this is telling us that this tangent line has the slope of 2. Okay, I'd like to work the same problem with the alternative rate of change. Let's go ahead and do that. So I'm going to take the limit as x approaches 1. Remember, there's no h in this alternative. And then I'm going to write x squared, because it just says put x into the function. Now put 1 into the function, so this will be 1 squared all over x minus 1. All right, the strategy is a little different now. I want to use my algebra technique, and in my algebra technique I'm going to factor, and I hope that looks familiar to you. I'm going to go off to the next page, and you can see that I can reduce and then actually take the limit. And we're getting the same answer too. We're getting that the slope here of the tangent line at 1 is 2. All right, now what if I ended up giving you this limit expression Do you think you could identify the function? Do you think you know what function I'm working with? And so again, here's the function right here. All right, and it looks like the number being used, this A, is the number 2. So I think I'm going to say the instantaneous rate looks like it's at 2, and the function looks like it is 5 natural log of x. That's we're putting the number 2 in for x, and we're putting the number 2 plus h in there. Okay, let's take a look at this one. This is the alternative form here. This looks like this one right here, and it looks like I can tell what my f of x is. It's this guy right here. So my f of x is sine of x, and then it looks like I can look for my a. My a will be right there, and so that'll be at pi halves. And so if I give you the limit, can you tell what the function is I'm working with, and can you tell the instant at the point I'm looking at? Okay, and this is the end of the screencast.